By the way, what is differential? A differential is about a change. In your daily life, you can see everything is changing. And very simple and like common example is the population. I am in Wuxi, and 10 years back, the population was less. And now the population is increasing, and every day it is increasing. So, the population is changing. And why the population is changing? What are the ingredients which are provided to the population and then the population changes? The first ingredient is the environment, the food, water, and a feasible environment. And what do you say? We say that if we have an ideal environment, then this population will grow up, the population growth. And if we have a bad environment, we don't have an ideal environment, the population will drop, the growth will be negative, the change will be negative, because people will die because of hunger. If there is no ideal environment, there is no food. If there is no food, the population will reduce, the people start dying. Population is not about the human being, it is about every living being. And every living being needs what? The basic thing? Water and food. If there is no good environment, there is no water, there is no food, then the population will reduce. Now these are the ingredients, but there is an important factor on which the growth of population is dependent, and that factor is time. Whenever you talk about the growth of population, you talk about time. If I say that in 1990, the population of Wuxi was 1 million, and in 2021, the population of Wuxi is 10 million, then what I am actually talking about? I am talking about the time. This population has a direct relationship with time. This population is dependent on time. So the change in population it's actually depending on many factors. The growth depends on many factors, and it depends on food, it depends on water, and so on. But mathematically, the change, growth means change. A change in population, it depends on time. Whenever you will talk about change in population in the form of differential equation, you will talk about change in P with respect to the time t. So what does this mean? It means P is a variable and this P is a variable which is further dependent on the time. So P is a variable because the population P changes with the passage of time and it is dependent on time. So P is a variable and it is dependent on time T. Also T is also changing. Every second T is increasing, T is changing. but this change is always linear with a constant ratio, and t is not dependent on anything. Whatever happens in the world, the whole world blast, the time will continue, time will change, time will not stop. So it means time is not dependent on anything else. That this time is also a variable. This p is also a variable, but this p is dependent on the time. If the time stops, the change in population will stop. But time is not dependent on anything. Whatever happens, time will continue. Time is changing every day. So this t is also variable, but it is an independent variable. This p is population p is also variable, but it is a dependent variable. And for this case, it is depending on time. T is also variable, and for the scenario, T is not depending on anything. Whatever happens, whatever is happening in the environment, T will continue changing. The change in T will continue. So, the first thing you must know when you start talking about the differential equations is the dependent and independent variable. A variable that further depends on another quantity. Independent variable a variable that do not depend on any other quantity. So, a dependent variable was the population, and it was depending on the time. An independent variable was time, and it is not depending on anything else. Population will change if the time change. Time will change whether anything else change or not. Is it okay? Is it good? So, the important section of this single variable calculus is differential equations, because every problem in the real world situation is actually written in the form of a differential equation. And I already told you the first example, the population growth. When we talk about the population growth, we talk about a differential equation. And in this scenario, we will write the population P as P equals to P of T. This P is the total population, and this is depending on the time t. And if we want to write this equation in the form of a change, then we will write a change in this p, it means the population, the total population. If I'm talking about a change in this population, then I will write a dp, a change in population, with respect to what? Because p is dependent on the time t, so I will write a change in, del p. You are familiar with this del. This del was actually a change in step. You were standing here and you moved to here, you change your position. And I said that this change in your position, one step was actually a del x, a change in your position. So that is del p means a change in population. And this del p, when we switch into the integral formula, we said, okay, this del p is similar to dp. So this dp is coming here. And why this dp? Because the time is changing, so there is a dt. So when you talk about a change in population, you will write dp by dt. And this dp by the change in population is directly affecting the total size of the population. If the change is positive, the total population will be increasing. The total population will increase. If this change is negative, if the bad environment, if there is no food, there is no water, the total population will decrease. So it means this dp by dt is directly affecting the total size of the population. So that is why we are writing a directly proportional relationship between these two quantities. This p is the total population and this is the change in population, and both are directly connected with each other. So if you want to remove this constant of proportionality, the sign of proportionality, you can place a constant k, a constant of proportionality, into the p. This is an equation, a differential equation for the population growth. Now, I have written a formula for the change in population. So, the important thing here is actually this k. So, actually, whatever will happen with the population is linked with the value of the k. There are three possibilities for a real number. It can be 0, it can be positive, it can be negative. So I am considering all the three possibilities for the real number k. If this k is 0, then the equation dp by dt equals to 0. This means dp equals to 0. And when you integrate this equation, it means p is a constant. So, if the value of k is 0, then there is no change in the population. There is no concept of population growth or decline because the constant k is 0. So, if k is 0, there is no change. If the k is positive, then dp by dt equals to positive k into p, and this positive k into p means the total population P will be changing, P will be positive. It means dP by dt is greater than 0, and this means the change in population is actually a growth because the population is increasing. So in that case, I can say that the population graph is actually increasing exponentially. This was the initial population. With the passage of time and with the values of the k, it starts increasing this way because the change in population is directly proportional to the total population. If the value of k is negative, if k is less than 0, then dP by dt equals to negative value of k, and it will be less than 0. It means the change is negative. So initially, if I was here, then the change will be like this. So the population graph is exponentially decreasing. Here the population was exponentially increasing. So from here, this scenario, I can assume that a change in population is actually an exponential growth. If the environment is not good, it will be decreasing exponentially. And if the environment is good, it will be increasing exponentially. The change in population dP by dt is an exponential function, and this exponential function, because they are directly related with each other. Any question? Another example is motion of a mass connected with a spring. Have you heard about it? If this is a spring, this is the rest position of the spring. This point is 0, and the spring is actually in the, if you put it on the ground, it is like just like this. This is the rest position of the spring. What I do, I connect a mass. Now this spring is hanging with the, let's suppose, with the roof. Now what I do, I connect a mass here. When I will connect a mass here, this spring will stretch. Now this is a mass. So actually what happened? There is a change in the position of the spring. Initially it was here. Now from here it is now at this position. So this is the change in the rest position of the spring. So I can say this is the change in the position of the spring, that is x. Hooke's law is that a force is linked with negative k into x. This change in the length of the spring is actually linked with a force which will try to pull back this spring to the rest position. Now this spring was hanging with the roof, so gravity is affecting on it, and this gravity when something is falling down, the gravity is positive. Now there is a force in the spring which is trying to pull back the spring to the original position, and that force is F, and this force is written by this formula. By this is negative k of x, because the force is trying to pull something away from the gravity. That is why there is a negative. This formula was given by Hooke, and this formula expresses this scenario. Then what is force? Force is mass into acceleration minus kx. What is acceleration? Acceleration is a derivative of the velocity with respect to the derivative of time. It is equal to minus kx. This derivative of velocity is the velocity is further derivative of the position, and this is equal to minus kx. So it means md square x by dt square equals to minus kx. So actually the scenario was not in the form of a differential equation. It was f equals to minus kx. But the hidden words say that this scenario is actually in the form of a differential equation. You can see a differential here. So every real world problem which possesses a change is actually written in the form of a differential equation. Now, in previous example, we were having dp by dt equals to kp. So there was one power of d. So it was the first order differential equation. Now you can see in the spring constant, it is d square x by dt square. So the power is 2. So this is a second order differential equation. An equation that involves a function, say y equals to f of x, and some derivative of the same function y equals to f of x is called a differential equation DE. So if f of x is a function, then f dash of x is the derivative. So a solution of a differential equation is a function y. If your differential equation involves the function y, then its solution will be, if differential equation is like dy by dx, then the solution will be a function y that satisfy the differential equation. You are claiming that this y is the solution of your differential equation, then you can put this y into your original equation and check. If the equation is satisfied, then yes, this y is the solution. Equal now kc e raised to the power kt. It was like this. Now, if I say that assume, so far we have not tried to solve this equation. We are just trying to know about this equation. So if I assume that, let's suppose p equals to ce raised to the power kt. If I assume that this is the solution of, this is my equation 1, and this is the solution of 1, then what should I do to check whether this is the solution of this equation or not? I can simply put the values, these values in this equation, and I can check how to put these values. I have kc e raised to the power kt, that is fine. Where to put this p? I can put this p here. So it means I will differentiate this thing with respect to t, and whatever comes is actually this one. So if about how to differentiate this equation, it is simply d by dt of this thing ce raised to the power kt, and this will be kc e raised to the power kt. Now I have this thing, I can put it here. It will be kc e raised to the power kt from here equals to kc e raised to the power kt. These cancelled out, so 1 equals to 1. So the equation is identically satisfied. So it means, yes, initially I was claiming that this is the solution of this equation. When I checked, I found out that the equation is satisfied. So yes, my claim was right. This is the solution of this differential equation. Question is, if the differential equation dy by dx is 1 by 2 y square minus 1. This is the differential equation, and let y equals to 1 plus c e raised to the power t over 1 minus c e raised to the power t is a solution of the equation 1. The question is, check what? Check that this is the solution of this equation or not. Now this, if I am done, I have checked that okay, this is the solution of this differential equation 1. Now I am confirmed that okay, this is the solution. Then this is the solution for all the possible values of t. For all the values of t, this solution justifies this equation. Now the part B is that if you have a certain value of t, and at that certain value of t, the value of y is given, if y of 0 equals to 2 means at t equals to 0, y is 2. Now if you have this data, then you can find out this constant c. So you can plug in these values here in the solution. Y is 2. It is 1 plus, I have to find the c e raised to the power 0 divided by 1 minus c e raised to the power 0. And this means 2 into 1 minus c equals to 1 plus c. And from here, I can see that c is 1 by 3. So for a specific value of t, the corresponding value of y is 2, and this gives me the value for the c. So I can write that for the differential equation 1, at y of 0 equals to 2, the solution of the differential equation is 1 plus 1 by 3 e raised to the power t divided by 1 minus 1 by 3 e raised to the power t, and you can further simplify this thing. So if I have some initial data, then I can find out this constant which is coming because of the integration into the solution. Why this constant is coming here, this we will discuss in the when we will be able to solve a differential equation.